Hey everybody, welcome to tutorial 26. In this video, I'll show you an approach that I like to use for applying granular synthesis to a live audio signal. Once again, I'm going to be using my voice as the thing we're going to granulate, so before starting this recording, I grabbed a microphone and an audio interface and connected them to my computer. I assume most people watching this video are already familiar with this kind of setup, but if not, I've covered this process in tutorial 20. And as a reminder, whenever you're coding with a live microphone, it's usually a good idea to use headphones to avoid feedback. So before booting the server, we'll get a list of the available audio hardware and set the server's input and output devices appropriately. And just to confirm that our signal flow and gain stages are all in good shape, I'll build a quick sound function that uses a comb filter to apply a feedback delay to the mic signal. Testing. One, two. Fantastic. If you watched the previous video on GrainBuf, you might guess that we're going to use GrainIn to granulate the mic signal. And in fact, that's a pretty logical guess, considering its description. However, if you look more closely at the help file, you'll see that GrainIn doesn't have quite as many arguments as GrainBuf. In particular, it's missing grain playback rate and grain start position. And this means we can't really use GrainIn to do any sort of pitch or time manipulations like we did in the last video. All things considered, GrainIn is pretty simple. The main thing it does is apply little grain windows to an input signal, allowing those parts to be heard whenever we get a trigger. Just to demonstrate, here's a simple example with approximately 20 grains per second, each one 0.08 seconds long. And it sounds like this, where parts of my voice come through as grains and other parts don't. And it occurs to me, GrainIn by itself is essentially kind of a glorified envelope generator. For example, if we swap GrainIn for envgen, specify a sinusoidal shape 0.08 seconds long, and re-trigger the envelope in the same way, we get almost exactly the same sound. It's pretty much indistinguishable from the first example. So it's not that GrainIn is totally useless. You could certainly combine it with other signal processors like delays and filters, maybe some iteration or multi-channel expansion, whatever. But I don't think GrainIn quite gives us the flexibility we want. So then the question is, how are we actually going to implement this? Well, once again, we're going to use GrainBuf. But in contrast to the previous video where we just had one SynthDef, here, the configuration is necessarily a bit more complex, and in fact, it's going to involve several different SynthDefs that work together. To help explain how it's going to work, here's a visualization. First, we allocate an empty one-channel buffer, just a block of memory where we can read and write audio samples, let's say 5 seconds long. And then, in terms of signal processing, we'll have 4 discrete parts. Number 1, a SynthDef that uses sound in to read a signal from audio hardware and writes it to a bus so that other processes can access it. Number 2, a SynthDef that generates a periodic ramp and writes that signal to a different bus. Conceptually, the output range corresponds to the size of the buffer, with the duration of one complete cycle being equal to buffer duration. Number 3, a SynthDef that reads the mic signal and ramp signal from those 2 buses and records the microphone signal into the buffer using the ramp as a sample index. Because the ramp signal periodically repeats, this means that when we reach the end of the buffer, we automatically jump back to the beginning and overwrite old samples with new samples. Finally, number 4, a SynthDef that uses GrainBuf to generate grains from the contents of the buffer. For the grain start position, we use the same ramp signal, but we subtract some amount from that signal. Use a modulo operation to wrap the result within the appropriate range, and in effect, we get a grain start pointer that tags along behind the record pointer, sort of endlessly chasing it around. There's a few interesting variations on this idea. For one thing, we could add a little randomness to the grain pointer so that it skitters around as it moves, and this will have the effect of jumbling syllables and generally making the recording less intelligible. And another variation, just because we only have one GrainBuf SynthDef doesn't mean we're only allowed to make one synth. For example, we could make 5 synths, so that we have 5 grain pointers, all generating grains independently, all following behind the record pointer. Now, you might be wondering, why bother anchoring the grain pointer to the record pointer at all? Can't we just pull grains from anywhere in the buffer? Well, technically, yes, you can, but this brings us to the main pitfall of this approach. At any point in time, there's almost guaranteed to be a discontinuity in the buffer at the record head, right between the oldest and newest recorded sample. And if we ignore this discontinuity or don't properly factor it into our algorithm, for example, if we generate a grain that is longer than the distance between these two pointers, then that grain will include the discontinuity and we're likely to hear a big, ugly click. And generally we try to avoid this because it sounds bad. And just in case you don't quite know what I'm talking about when I say big, ugly click, here is a sample of me talking, or that sounds like this could exist. And here's an example of what a grain might sound like if you fall into this trap. And I'm going to intentionally make this click sound fairly egregious. It's not good. So generally, this is why we tether the grain pointer to the record pointer, basically so that we have a strong guarantee that grains won't spill over and collide with this discontinuity. So with that introduction out of the way, let's turn these ideas into code. First, allocate an empty buffer. So b equals buffer.alloc, name of the server, and number of frames. So for 5 seconds, we do s.samplerate times 5. Keep in mind, this duration is mostly arbitrary. You could make it smaller, although it might get a little claustrophobic around 1 second or so, but larger is certainly fine. So 30, 60 seconds, especially if you want to capture a recording of stuff that happens over a relatively long period of time. Third is the number of buffer channels. We want 1. 1 is also the default, so technically we don't need it, but I'm going to leave it here for clarity. Next, we need 2 one-channel audio buses, 1 for the mic, 1 for the pointer. And again, 1 is the default for number of channels, but I'm going to type it in anyway. And now we're ready to start building SynthDefs. First, a SynthDef called mic, which simply reads a signal from a hardware input bus with an amplitude control just in case we want to mute or adjust the level, and out it goes onto a bus. That's it. Next SynthDef, called pointer. This one will use phaser with very much the same technique we saw in the previous video to generate a repeating ramp to index into the buffer. And unfortunately, I made a mistake in the previous video. It wasn't so much of a big deal in tutorial 25 with pre-recorded sound, but here in a live context, it is a big deal. In the help file for phaser, we note that the end value is defined as the wrap point, which means the ramp it generates goes up to that value, but is never actually equal to that value. So for the end value, we need buff frames, not buff frames minus 1, as I did in the last video. I apologize, that was my mistake. Also, just a quick note that I'm not really thinking about these argument values right now. These zeros are just placeholders. We'll make sure to set these correctly when we actually start instantiating synths. Third, a SynthDef responsible for reading the mic signal, reading the ramp signal, and recording into the buffer. So here's our pointer, here's our live sound, and buff right to record sig into buff using pointer as the sample index. Conspicuously, there's no out.ar here because this SynthDef doesn't actually output a signal. Its only job is to record a live signal into a buffer. And finally, number 4, the granulator. Now these first 3 were pretty simple. This one's going to take a little more work. Fundamentally, I'm going to base this off the one we saw at the end of the previous video, but with a number of changes to accommodate real-time considerations. So first, I'm going to paste in the easy stuff. We have an envelope for overall amplitude, a basic attack, sustain, release shape that can be held open with a gate. And basically, this just gives us an easy way to turn granulators on and off with a nice fade in and fade out. Grain density control, exactly the same as it was in the last video. Grain duration control, also exactly the same, except I changed this argument name from dur to base dur. Rate control, here I've decided to multiply by a noise generator so that the overall playback rate can be randomized within a range. And pan control with a base pan value and a random amount of spread. And now we're going to incrementally add in the new stuff, which is going to be mostly focused on the grain pointer, how it interacts with other parameters, and just generally making sure that our grains don't have clicks. To start, we need to read in the pointer signal. So in.ar, adding a new pointer variable and pointer bus along with it. As we saw in the visual demo, the grain pointer lags behind the record pointer by some amount, so let's declare an argument to represent that value. For a sensible default, I'll arbitrarily say 20,000 samples, but we can change this at instantiation time if we want. And at a very basic level, what we want to do is subtract this delay from the sample pointer. So that would look like this. And then because GrainBuf expects a normalized pointer between 0 and 1, divide this value by the number of frames in the buffer. But there's an issue we need to consider here. Let's imagine a specific moment in time when the pointer signal is at 0 or just slightly above. If the pointer delay is 20,000 samples or some other large number, then the end result is a negative pointer value. But GrainBuf expects something between 0 and 1. So probably a good idea to wrap this value between 0 and 1, which we can do with pointer.wrap 0, 1, or alternatively, we can take the pointer value modulo 1, which has the same effect. This being said, it seems GrainBuf actually does this modulo operation internally, as we can demonstrate with a quick sound example. So here's that short sample of me, or that sounds like this could exist. And here's a simple GrainBuf example. The grain position is 0.6, and as long as we change this value in increments of 1, even going into negative values, the results are identical. So I'm pretty confident that putting a modulo operation in the SynthDef is technically not necessary. Now, if we want to implement that random skittering pointer effect, we'll need a noise generator, which I'll call pointer rand. And I'm going to give this a default range of 5,000 samples. And because there are now two things affecting grain pointer position, I think it would be convenient to create a variable that represents the total number of samples we're going to subtract from the incoming pointer. So the total number of samples we subtract is equal to the base sample delay amount minus the pointer randomness. And then down here, we're going to subtract the total delay from the pointer. Now here there's another possible issue. There's nothing in place to prevent the user from specifying a small base pointer delay and a large amount of randomness, in which case total delay would often push the grain pointer forward in such a way that we'd very likely be capturing the buffer discontinuity in the grains, and that's what we're trying to avoid. So it'd be a really good idea to implement some sort of safety mechanism that forces total delay to be greater than some established minimum. And a very easy way to do this is to use max, which compares two values and takes whichever is greater. And I do recognize it's still possible to break this code by putting like a negative value here for min pointer delay. We could try to anticipate every possible careless thing the user is going to do, but I got to draw the line somewhere. You know what? If breaking this code makes you happy and gets you up in the morning, go for it. Live your best life. So now that total delay is guaranteed to be greater than or equal to min pointer delay, we have a nice, healthy looking grain pointer. The last piece of the puzzle has to do with grain duration. Basically, the grain pointer is behind the record pointer by some amount of time, and that distance determines the maximum grain duration. So it's tempting to build a similar safety mechanism that uses min to compare the user-specified grain duration and the actual amount of time between the pointers, and then take the smaller value. But, if only it were that easy. Well, it's actually pretty easy. It's just a tiny bit more complicated. We also have to factor in grain playback rate. And to demonstrate precisely why grain playback rate needs to be factored into this process, here is another visual demonstration, in which we imagine that this is our 5-second buffer being filled and granulated in real time, and we've magically hit pause on this process and are now looking at a moment frozen in time. Our record pointer, and therefore the buffer discontinuity, is right here. Let's say about 2 seconds from the beginning. The oldest audio is here, about to be overwritten, and the newest audio is here, freshly laid in a mere second ago. And let's also imagine that at this moment, the grain pointer is behind the record pointer by half a second. So we're about to produce a grain. Let's say the algorithm requests a half-second grain with a playback rate of 1. Well, that's no problem. We just read this half-second chunk and we're done. But now instead, let's suppose the algorithm requests a half-second grain with a playback rate of 2. Now you might suppose that GrainBuf carves out a half-second chunk and then resamples it at twice the speed. But this is not what actually happens, because in this case we wouldn't get the half-second grain that we asked for. This grain is only a quarter second long. What GrainBuf actually does is it carves out a chunk of the buffer equal to grain duration times playback ratio. So in this particular case, twice as much. It then resamples in order to give us the correct grain duration and correct playback rate. And as a consequence, we've inadvertently included the discontinuity in the grain. So the takeaway here is that even if we ask for a grain duration that is equal to or smaller than the distance between these two pointers, we can still accidentally bonk into the discontinuity if the playback rate is too high. And while we're here, you may already be able to see that pitch shifting up is the problem case, while pitch shifting down with ratios less than 1 is actually pretty harmless. For example, if our specified playback rate was 0.5 instead of 2, then GrainBuf only needs to take half as much audio and then stretches it out by a factor of 2, and the discontinuity is not a problem. So that is why it's necessary to account for playback rate in order to avoid unwanted clicks. So what exactly do we do to this SynthDef? Well, feel free to pause the video here and see if you can work out the solution on your own. In fact, I recommend you do so because I think this is a good opportunity for a little self-learning exercise. There are probably a few different ways to express it, but I've chosen to do it like this. The maximum allowable grain size is equal to the total pointer delay divided by the grain playback rate. And because this is a value in samples, divide by the sampling rate to convert to seconds. And then we use min to take whichever of these two values is smaller, and the result is the actual grain duration. And now there's just one more thing we're missing, and that is GrainBuf, filled with all of our meticulously calculated control signals. So that wraps up the SynthDef creation process, and we're now ready to start placing synths on the server. If you recall tutorial 7, you'll remember that when we're using buses to pass signals from one synth to another, as we're doing here, any synth that writes to a bus needs to be upstream of any synth that reads from that bus. In this particular case, we need the mic and pointer synths to be upstream of the recording and granulating synths. I'm going to use groups to manage node order. Specifically, I'm going to make 4 groups, 1 for each type of synth, placing each one after the one before it. Keep in mind this is not the only way to do it, but it seems sensible to me. So, a mic synth, writing the mic signal to mic bus, placed into the mic group. A pointer synth, which needs to know which buffer it's indexing, writing a ramp signal to pointer bus, placed into pointer group. And a record synth, which needs to know the 2 input buses it's reading from and which buffer it's recording into. Place that in its correct group as well. We're not done yet, but let's run these 3 lines anyway. The node tree looks good. We don't hear anything because currently nothing is sending signal to hardware output buses. But right now, in fact, we are recording my voice into buffer B, and to verify this, we can plot it. There's definitely something there. And if you want, you can even play the buffer to hear what's in it. And although you can evaluate b.play right here while all this is happening, for clarity, what I'd prefer to do is first free these 3 synths. I could hit command period, but that'll remove the groups too. So to free all the synths, but leave the groups intact, we can do s.defaultgroup.deepFree, which is pretty convenient. And now let's play the buffer. Intact. We can do s.defaultgroup.deepFree, but leave the groups in. Everything seems to be working. We're successfully writing audio into the buffer. Cool stuff. Let's clear everything out of the buffer with b.0. Good as new. Now for the final ingredient. We'll create a granular synth, drop it into the appropriate group, and give it a short name so we can talk to it more easily. To save time, I've copied and formatted all the SynthDef arguments ahead of time. So I'm just going to paste them here. A lot of these default values, we can just leave them as they are, change them as desired, but there are a few we need to address up front. In particular, we need to specify the buffer to granulate, so buff B, and we also need to make sure the synth is reading the pointer signal from the correct bus, so tilde pointer bus goes here. Now, in the interest of starting with a relatively simple sound, I'm going to zero out the pointer randomness. So the grain pointer is smoothly following behind the record pointer, just maintaining its distance. And this 20,000 is fine, but it was kind of a placeholder, so let's be more precise and make the grain pointer lag behind by exactly 1/3 of a second. And before you run this code, I'm just going to issue one more warning. Make sure you've either got headphones in or otherwise have your feedback situation under control. All right. Like I said, this configuration produces a fairly simple sound. We're doing 40 synchronous grains per second, each one 1/20th of a second long, so they overlap in a very precise way. And as a result, we reconstruct the recorded signal very accurately, with a 1/3 second delay, of course. Let's fade this out by closing the envelope gate. So all we've really done so far is make an unusually complicated delay line. But now we can start having some fun with these grain parameters. For instance, let's bring back that pointer randomness, deviating by up to a 1/6 of a second in either direction. And for ease of code evaluation, let's detach this clump and put b.0 at the top so that we're clearing the buffer each time we start up a new granulator. So even with this relatively small change, we've created a considerably more interesting granular effect. But of course, there's no reason to stop here. Let's randomize the playback rate within a range of 2 semitones, up and down, and also create a more interesting stereo image by widening the amount of spatial randomness. So now we've got a jumpier sound, more variation, more changes, that sort of thing. You know, getting some good use out of these granular parameters. Now think back to that first visual example where we had 5 independent grain pointers, all anchored at various distances behind the record pointer. Let's turn that into a reality. So what I'm going to do is use collect to generate 5 synths, put them in an array, and store the array in the variable g. And since we're making 5, we'll dial back on the amplitude. Let's randomize the grain densities a bit, also increase the base grain duration and randomize that by a factor of 1.5. Now it'd be kind of redundant to have all 5 pointers clustered around the same spot in the buffer, so let's space them out. Inside this collect block, the argument n is going to be equal to the integers 0 through 4, so we can use this value along with lin to easily place the grain pointers at specific spots. Now the whole buffer is 5 seconds long, and I don't want to go back in time too far, so let's say the first grain pointer will be 20,000 samples behind, and the last grain pointer will be 2 seconds behind, with these 5 pointers linearly distributed across that distance. And let's have each pointer wiggle around by 10,000 samples in either direction. And you know what? Let's do a similar thing with amplitude, so that the grains that are closer to the record pointer are louder, and grains that are farther behind are quieter, which should sound a little more natural, maybe a little less chaotic. So I'm going to map the iteration count linearly onto decibels, and then convert from decibels to amplitude. And because G is now an array of synths rather than an individual synth, g.set won't work anymore. So let's prepare another line of code that will iterate over the array and close the gate on each synth. So this is what it sounds like. Kind of a psychedelic echo effect. That covers the basic functionality of the live granulator. So from here, let's do a couple variations. First, I want to make a granular freeze effect. In other words, apply a granular sample and hold technique to a very short segment of sound. The main thing we need to do is give ourselves a way to pause and resume the pointer signal. And the easiest way I can think to do that is to go back to the pointer SynthDef and add a rate argument. And to verify that it works, let's temporarily poll the signal so we can see the values. Instantiate a synth using this modified SynthDef, and we can zero the rate, therefore freezing the pointer, by sending a set message to the enclosing group. So let's go back a few steps to where we had a single granulator instead of 5, and make a few changes to give the granular freeze effect a nicer aesthetic. So sensible amplitude, dense asynchronous grains, stabilize the grain duration at 0.1, remove the playback rate randomness, fix the pointer delay at 10,000 samples, and minimize the pointer randomness. Okay, so now we can use a set message to free... I was saying we can use a set message to freeze the grain pointer, and then we get stuck on this one specific chunk of audio. And from here we can unfreeze the pointer by setting rate back to 1, and things keep moving along. This freeze effect gets the job done, but it isn't perfect because we're taking a short and kind of sloppy approach. By doing a hard stop on the pointer, we're disrupting the recording process. But even though the pointer stops, sound keeps happening and real time keeps moving forward, which means we're actually introducing a discontinuity into the buffer, and we might hear a few clicks when the pointer resumes. So if this bothers you, one solution would be to somehow build in a buffer crossfade whenever the pointer stops or starts, or alternatively, allocate multiple buffers. So after you do a freeze, you resume the recording and granulating processes using a new empty buffer, and once that takes over, you can fade out the old frozen one. Let's do one more variation and see if we can make a half-decent real-time harmonizer. Now, as we saw in tutorial 25, some of the recommendations for optimizing a clean granular pitch shifting effect are to use dense, asynchronous grains, a relatively large grain size, and let's start by pitching down by 3 semitones. Let's also remove this panning randomness. As for sample delay, we probably want this delay to be as small as possible because we want to hear the harmonization immediately, as soon as we start making sound. Now, our SynthDef safety mechanisms should protect us from hearing any buffer discontinuity clicks, but nevertheless, we can do the math ourselves. So our grain size is 0.2, converted to samples, and then scaled by playback ratio. This makes our pointer delay only as big as it needs to be. As for pointer randomness, I don't think we'll need any. A small amount probably wouldn't hurt, but for now I'm just going to leave it at 0. Let's try it out. Well, it sounds like this. And as you can hear, there's quite a noticeable amount of latency between my voice and the harmonized voice. If we want to reduce that latency, one thing we can try is reducing the size of the grains to something that produces a more tolerable amount of latency, like 0.07 seconds maybe. And this is definitely an improvement in terms of latency. Still an audible delay though, and in terms of sound quality, about the same, maybe a little worse. And in case you're wondering, we can't just drop the grain size to something microscopic because then the grains are just too short and they'll start sounding kind of glitchy. For sure, this is an interesting effect, but not a good harmonizer. And in fact, in this case, our pointer delay is less than min pointer delay. So min pointer delay is taking over, overriding this value and imposing 1,000 samples worth of latency, even though it's more than we actually need. As I was writing this tutorial, I was messing around, and there is a kind of a cute trick to help reduce latency. So we go back to our granular SynthDef, and basically we're going to disable our safety mechanisms. So these 2 lines that constrain grain duration based on available space, comment them out. And the other safety mechanism for total delay, well, min pointer delay is an argument, so we can manually set that to 0 ourselves. In making these changes, the SynthDef is basically saying, hey, you want to avoid grains with clicks in them? You're on your own. Do the math. You figure it out. So back to the synth, set the grain duration to be some sensible size, like 0.1, and set the pointer sample delay to be, you know what, let's do 1 sample, the smallest increment of digital audio. This means the grain pointer is right behind the record pointer, like practically right on top of it. So let's run this.
And you can hear that the latency is extremely low. I would say completely negligible. Now, we've got our safety mechanisms off, and 0.1 second is definitely longer than 1 sample. So a reasonable question is, how in the world are we not bumping into the discontinuity? Like, shouldn't we be hearing a bunch of gross, clicky audio?
Well, no, actually. The secret ingredient is we are pitching down. And as demonstrated in that second visualization, we really have nothing to fear when the playback process is slower than the recording process. Because remember, all of this is happening in real time. So we start making a grain and we're reading the buffer samples at a rate slightly slower than normal, but the recording process is going along at normal speed. So by the time the grain is finished, all those samples have already been filled in by the record pointer. So generally speaking, if you're pitching down, you have virtually nothing to worry about. Now, pitch shifting up, well, that's a different story. Let's go up by a mere 1 semitone and keep all the other settings the same. And wow, it sounds like absolute garbage. In this example, the playback process is happening faster than the recording process. So fast, in fact, that it's catching up to the record pointer and going past it. And that's not good because we don't have a time machine. We can't know what happens before it actually happens. So GrainBuf just blindly charges forward and suddenly it's capturing the buffer discontinuity along with stuff that happened 5 seconds ago. And well, it's just a complete mess. The reality is that a delay of 1 sample is just not enough space if we want to shift up by 1 semitone. So a very good question is, what is the minimum amount of latency we need to impose in order to avoid this obnoxiously repulsive sound? Well, I believe it works like this. Our grains are 1/10 of a second long, so the amount of buffer that GrainBuf takes is this value times playback ratio. And because both of these pointers are moving forward at 2 different rates, we don't need this full delay amount. We only need the difference between this modified duration and the duration at normal speed. Convert this to samples and evaluate. So in my case, 263 samples should do the trick. And there you go, pitch shifting up by 1 semitone with minimal latency. If you want to go up by more than 1 semitone, we can't just change the rate and leave everything else alone. It's no good. We are back in garbage town. To do this correctly, we'd also need to redo this calculation and increase the pointer delay as necessary. And now we're up by 2 semitones, and still we have a respectably small amount of latency. So it is possible to harmonize up, but the higher you want to go, you're just going to have to eat more and more latency. So you just got to make the call for yourself. How much latency are you willing to accept? And that determines how high you can go. Now basically, if you can adapt your creative workflow to favor downward pitch shifting whenever possible and harmonize up only when absolutely necessary, then you're in a pretty good spot. That being said, let's go back to our multiple synth example using collect. And here's a version that creates a real-time harmonized chord. Harmonizer. Or we could change these pitch values to do something a little more dissonant and sinister.
We are the Borg. You will be assimilated.
It's worth pointing out that there is a UGen called Pitch Shift, which is a granular-based harmonizer, and it's basically optimized for this sort of thing. I recommend trying it out. You might find the sound quality to be good enough for some applications. With granular harmonizers, you're always going to have some flavor of imperfection and digital artifacts, but using pitch shift is certainly less work than putting all this business together. However, if you're looking for a broader and more multi-purpose palette of real-time granular textures, I think the approach we've covered here is well worth the effort. That's it for tutorial 26. I hope this video helps you understand the principles of live granular synthesis on a deeper level, and I hope it gives you some useful tools and exciting ideas for your own creative work. As always, if you have any comments or questions, please feel free to leave them below. Thanks for watching. I'll see you next time.